Hello, and thank you for joining our webinar. Our training outline will include an overview of analytical to method development, how to create analytical scouting runs, common calibration errors, how to look for chromatography issues before the scale up to the preparative system, and troubleshooting common problems. Although we will use the time on target algorithm built in the Teledyne ISCO systems for many of our examples, most of the information applies to other method development techniques that you, the chemist, might use. The chromatography works the same, so the problems and the resolution are also the same. After the calibrations for each algorithm are done, the methods generally converge to the same solutions, such that the scouting gradient should generally be run the same way, no matter which gradient calculation you choose. We will discuss each of these techniques and describe how they work. We will discuss the advantages and disadvantages of each. Note that chromatographic issues and problems with one of these techniques will generally apply to the others as well. You can't calculate a gradient from poor chromatography, and we will show you how to recognize situations where the calculated gradient can't do a good purification. All of the techniques work best with matching analytical and preparative columns to maintain the same selectivity, as we will show later. All of the techniques need matching solvent systems between the analytical and preparative runs. One of the oldest models is the linear solvent strength model. It forms the basis of the dry lab software and some HPLC gradient calculation built into some systems. The linear solvent strength model is based on the displayed equation, where K is the retention of the compound compared to its retention in water, Kw, if the column is run in reverse phase. S is a constant and phi is the solvent composition. Different compounds will have their own lines based on their relative interaction with the column. In order to form these lines for an unknown compounds, there needs to be at least 2 scouting runs with different slopes. The multiple runs allow solution of simultaneous equations to determine the solvent composition for a desired K value, a desired retention time. It is more complicated to use this model in practice. There have been several refinements of this model over the years, but the original is still accurate for most compounds and purposes. Compound-specific method optimization is very commonly used. I see similar charts as shown in this slide in many labs. I tend to call it zones because the scouting gradient is divided into different zones. It is easy to understand, but it does take a bit of time to create the zones and methods. A change in either the analytical or prep system means the zones need to be created again because of differences in dwell and column volume. Each zone defines a different gradient method. Despite this name, this method isn't specific to any compound. This peak or this peak would elute early in the focus gradient and may not be well resolved from impurities, while this peak would elute late in the gradient. Another technique that is sometimes used is the accelerated retention window. C is the solvent composition to elute the compound at the desired retention time. RT is the retention time during the scouting run. B and delta are offsets to set the desired retention time and also include gradient delays. It can be very accurate, but a change in analytical or the preparative system or the scouting gradient requires determination of a new instrument constant. The other methods are very complex. The linear solvent model works best with multiple scouting runs for each purifications. The zones need the limits for each zone to be determined and tested. The accelerated retention windows algorithm needs the analytical dwell and column volume to be determined, and then a delta for the scouting run. A different scouting run needs a new delta. The time on target algorithm is a simple determination of all of the parameters with a single scouting run. It is built into AccuPrep systems. A change in gradient or a change in the analytical system running the scouting gradient only requires a new scouting run calibration. Like the linear solvent model and accelerated retention windows, the time on target algorithm calculates a focused gradient specific for the desired compound. So why would you use this method? The calibration is simple and needs to be done only once. A change to the analytical system only needs a scouting gradient run again for the calibration. If there is no matching analytical column, the scouting run can be run on the AccuPrep with the prep column and a small amount of sample. If you run the gradient calculation entirely within the AccuPrep, there is no calibration required at all. You can run this on the AccuPrep or use the data from an analytical HPLC using a scouting run commonly used to document a reaction so it works into your existing workflow. The focused gradient generator is very easy. You do a scouting run, select the peak you want to purify, and then purify the desired compound. Select the column and scouting method. A 150 millimeter long column will have a 6-minute gradient. Other column gradients will be in proportion to the column length. These scouting gradients have already been set up and calibrated for you. A completed run shows a focus button. Focus opens another screen. Choose the peak to be purified. Select a matching column for purification. Select the desired peak and press focus in the new screen. The system will generate a focus gradient centered on the desired peak. The compound typically elutes in 5 to 8 minutes on a 150 millimeter long column, and this increases resolution and allows higher sample loading. A wash step is included, which may be removed for more time and solvent savings if the sample is known to be clean. A focus gradient can also be created in the Q screen and run with other samples if an auto sampler is used. In general, the suggestions provided will help you whichever gradient calculation you choose. There is no need for isocratic holds because they add to the apparent gradient delay and waste time. Check for dwell volume issues on older HPLC systems. For a 4.6 by 150 millimeter column, a 6-minute gradient works well. When using Teledyne ISCO Universal Test Mix on C18, an elution greater than 8 minutes suggests too much system dwell volume. We can't determine accurate gradients for early eluting peaks very well if there is a large dwell volume. Increase the flow rate to 1.5 or 2 mils a minute to improve the calculation of gradients, but note the pressure limits on your column. If you are using multiple columns of different chemistries, if they are the same size and use the same scouting gradient method, you can use the same analytical calibration for all of them. In this example, a 4.6 by 150 millimeter column was used. The calibration was used peak number 3 at 5.27 minutes. Using the calibration peak will always create a correct scouting run since everything is calibrated on this compound. And note the changes with peak number 1 in the calculated gradient. As the gradient delay gets larger, the calculated gradient is a solvent composition with a lower concentration of B solvent. Peak 2 also sees deviation from the gradient that caused the desired retention as well. Many people tried to run the scouting gradient too quickly. These runs used a 2 by 50 millimeter UHPLC column. The 5-minute scouting gradient gave good results when run on a preparative column. But as the scouting run gradient became shorter, the calculated gradients no longer work very well, especially for compounds with high and low B solvent composition. These gradients fail to elute the desired compound very well. People often have an isocratic hold at the start of their gradients. All of the calculated methods assume some sort of apparent gradient delay, that is D sub A, even though it isn't explicitly stated in the calculation. D sub A is comprised partly of adsorption parameters, the chromatography, and partly mechanical. The mechanical portion is the draw volume of the HPLC and the column volume. Because of the apparent gradient delay, there is no need for an initial isocratic hold. If a compound elutes during the apparent gradient delay, it is going to be poorly retained on your preparative column. An initial isocratic hold increases the apparent gradient delay. This has an effect mostly on early eluting compounds. Early eluting compounds move down the column during D sub A. The apparently earlier elution causes the program to calculate a weaker solvent composition for the gradient, which causes later elution in the preparative run. The zone method is not affected so much because the zones can be arranged to compensate for the elution behavior of early eluting compounds. The initial isocratic hold still wastes time and solvent. Some older analytical systems have a large dwell volume. This causes a large delay as described on the previous slides. Also, gradient control is less precise. It is more difficult to create a precise gradient since the start and end of the gradient are not well defined. Some older calculation techniques describe the apparent gradient delay as a mixing volume delay. For the older HPLC systems, that was partly true. You can use a faster flow rate to reduce the delay, but remember to watch the back pressure so the column isn't damaged. The next few slides will show how scouting gradients can alert us to chromatography issues in the preparative runs. The most common one is pH control. A scouting and preparative gradient for quinine with no modifier is on the left. Corresponding runs with 0.1% trifluoroacetic acid, that is TFA, are on the right. Look for good peak shape. Look for fronting or tailing. In this case, the quinine was tailing and the peak came out too early without a modifier in the preparative run on the left. Adding a modifier gave good peak shape during the scouting run and very close to the expected retention in the preparative run. If it looks bad during the scout run, it will look worse in a focus gradient no matter what calculation method you use. Acidic compounds can also behave strangely. Here are scouting and preparative runs with salicylic acid and water methanol, but a TFA modifier was used again for the runs on the right. Again, the peak shape in the scouting run suggests that the preparative run won't work well. In both the acidic and basic compounds, the peak shape was improved and the gradient calculation worked better when a modifier was added to the mobile phase. The idea is to force the compound to be in one form or another, either all ionized or all as the free acid or base. On the AccuPrep, it is very easy to determine a focus gradient from an analytical HPLC scouting run. After calibrating the analytical scouting gradient, just run the same scouting run for your samples. enter the retention time for the desired compound, and the AccuPrep will calculate a gradient for you. Common method development problems include the pH might not be good for the compound chromatography as we just showed you. Verify the same solvents and modifiers are used in both the analytical and preparative system. Verify that matching columns are installed. Sometimes one or both columns will wear out, which will cause a change in retention time. If someone changed the scouting run, that will cause errors in method development. Changing an instrument means a different draw volume, so the gradient is delayed differently. One more thing that affects all gradient calculations is the use of non-matching analytical and preparative columns. All C18 is not the same. The runs used in the same scouting gradients in the example on the left. All of the columns were the same size and the same samples used. The elution on these columns is very different. The different retention times would generate very different solvent compositions for the preparative runs, which doesn't matter if the columns have matching chemistries. At this time, I would like to take questions.
Well, thank you, Jack. And I would like for you, if you have any questions, please enter the questions through the Q&A section within Zoom, and Jack will respond. Thank you.
Hi, Mahesh. I see someone has their hand up and I'm trying to see who that is. And if you can answer, ask your question, that would be Mahesh. Yeah, ask your question in the chat screen, we can answer it. But we do have one question is, can any of these scouting runs be used to predict loading capacity on your prep run? And the answer is, well, maybe. If the compounds are well resolved on your scouting run, they will be even more well resolved on your preparative run, so that you can then you can load it much more. Something that complicates the sample loading is the use of a strong solvent such as DMSO. I have a question about how do we calibrate the gradient selector on the prep instrument? If you are talking about the AccuPrep, the calibration is mostly programmed into it, and we have already done a lot of the calibration for you. To calibrate the %B that causes the correct elution time that you want, what you would do is you would do an Isocratic run until you get the solvent composition that causes the compound to elute at the time that you want. We have a technical note, Tech Note 52 on our website that describes the procedure for the AccuPrep. What should be my solvent composition for loading? The solvent composition should be as weak a solvent as possible to allow the sample to be focused at the head of the column. A lot of people use DMSO, and if the compound elutes with more than 40 or 50% B solvent for reverse phase, that works very well. However, DMSO is a stronger eluting solvent than water, so if you have compounds that elute in mostly aqueous mobile phase, the compound will tend to elute a little earlier and you will get peak distortion. Can you go from a gradient analytical run and select the focused gradient from that? And the answer is yes. That's what we've been doing, and we've provided a few different algorithms. How do we account for system draw volume variations? the draw volume variation is actually hidden in the apparent gradient delay. And the cool thing is that if you run a scouting gradient with a calibration compound, the draw volume is kind of mixed up in the apparent gradient delay, so you actually don't have to measure it. Okay, I see that your compound dilutes at 28% acetonitrile. Are we talking about a sample that you're trying to elute from a column? We can calculate a gradient for that, or if you're trying to do a calibration, that should work for most HPLC systems. In that case, if I use DMSO, then everything is coming in the solvent front. What I do then is compounds that are soluble in around 28% or elute at around 28%. I see this a lot with peptides, and what I might do is do an initial dissolution in DMSO and then dilute it with water. So I can get the sample fairly concentrated in DMSO and then dilute it in water, because if the compound elutes at 28% acetonitrile, the compound is usually fairly soluble in water. Another question is, can I use this technique to do solvent screening? In other words, run and try to test different solvents and different modifiers with analytical scouting runs? The answer is yes, you can. And as long as you use the same gradient method for all of your different solvents that you're testing, that is methanol, acetonitrile, with and without modifier, the answer is yes, you can. And then you can choose you can see which scouting run gives you the best resolution. Another question is, what if I'm interested in more than one compound? How can we handle this? The zone method won't handle that very well unless both compounds happen to be in the same zone. But the other methods work pretty well. And for the focus gradient generator on the AccuPrep, if the two compounds elute with a difference on your gradient of about 22% B, we can run them on the same gradient in general with a reasonable retention time. Any further questions, please?
Well, Jack, it looks like you have answered all of the questions. Oh, hold on. One just came in. If you can answer that question.
Yep, let me see it. Okay, Mahesh, I see your response. Yes, you mix water and DMSO and dissolve the sample in water first. I mean, in DMSO first, and then you can dilute it with water. And you could also, I suggest that you filter your sample as well. Okay, can I please clarify how I use the gradient selector on the prep instrument, please? We on the AccuPrep system, we have a scouting gradient that you would set up when you install a new column, and you just tell it that you need a scouting gradient to run, and you would ask it where you just enter where you want to start the gradient. For a C18AQ type column, you would enter, say, 0% B, since that can run in water. For regular C18 columns, I usually enter about 5% B as a starting point. And then when you run the column on the AccuPrep, you simply, when you choose the column, you can then choose the method, and the scouting run will be among those methods.
I do see there's a question if I can allow for someone to speak. Actually, all of the microphones for the attendees are muted, so I can't assist with that. If you care to, you certainly can contact Jack directly to discuss, to just further discuss your question. Jack, there is another question that came in after that.
Yes, I see it. Is the compound eluted better at isocratic or gradient in Prep LC? In general, you get better resolution isocratic. The focus gradient that we calculate with a range of plus or minus 5% gives resolution very similar to isocratic, but allows for some variation in, say, adding the modifier or some variation in temperature. The gradient is good at eluting compounds, and if you have compounds that are very, very well resolved with a lot of space between them, the gradient is very good at reducing the resolution between those two peaks if you needed to. Can you run the analytical scouting gradient on the inner shim? Actually, we can run the analytical scouting gradient on pretty much anything. We've run it on Agilent and Waters system, and we do run scouting gradients on the AccuPrep itself. Yes, you will get broader peaks in isocratic prep runs, but it's kind of a trade-off between how wide the peaks are and the resolution. So I see where you're coming from. However, on the scouting runs, if you can resolve the peaks on the scouting run, we can resolve them on the focused gradient. How do we account for differences in analytical systems when we use the auto prep? I suppose you mean the focus gradient. What we would do is just run a scouting gradient for each of your analytical system, and then enter the parameters, a calibration scouting gradient, and enter the parameters for your different systems. So if you have, say a Waters and an Agilent, I've got the calibration parameters for the scouting run for each of those on the side of my AccuPrep. And so whichever one I run, I then can enter that information on the in the AccuPrep and then calculate a gradient no matter where it came from.
If there are any further questions.
Oh, no, we got one more.
Okay.
Yep. How does an analytical scout calibrated to a focus gradient compared to the AccuPrep scout to focus? My experience is they work out about the same. In fact, we started off with doing the analytical scout calibrated to a focus gradient in the Journal of Combinatorial Chemistry paper that was cited earlier. And when we added the feature to the AccuPrep, we added in the gradient that is built in, the scouting gradient built into the AccuPrep to make it convenient for users. And then with the last software release, we were added the ability to use your analytical HPLC scouting gradient. This means that a customer doesn't need to run a scouting gradient on their analytical system just to see that, yes, they made a new compound and yes, there are contaminants in it, and then have to run another scouting gradient on the AccuPrep. The scouting gradient that they did as part of their workflow can be used for the AccuPrep.